A carboxylic acid (ＫRBKSLK) is an organic compound that contains a carboxyl group oxygen monohydride. The general formula of a carboxylic acid is RCOOH, with R referring to the rest of the molecule. Carboxylic acids occur widely and include the amino acids and acetic acid. Salts and esters of carboxylic acids are called carboxylates. When a carboxyl group is deprotonated, its conjugate base forms a carboxylate anion. Carboxylate ions are resonance stabilized, and this increased stability makes carboxylic acids more acidic than alcohols. Carboxylic acids can be seen as reduced or alkylated forms of the Lewis acid carbon dioxide. Under some circumstances they can be decarboxylated to yield carbon dioxide. Example: carboxylic acids and nomenclature. Carboxylic acids are commonly named as indicated in the table below. Although rarely used, IUPAC recommended names also exist. For example, butyric acid is, according to IUPAC guidelines, also known as butanoic acid. To more easily understand much of the below discussion of reactions involving carboxylic acids, it can be helpful to notice that the carboxyl group itself is a hydroxylated carbonyl group, meaning that two of the carbon atoms' 4 bonds are to an oxygen atom. The carbon atom's third bond is to a second oxygen atom, and the carbon atom's 4th bond attaches to R. The carboxylate anion RQ- is usually named with the suffix -ate, so acetic acid, for example, becomes acetate ion. In IUPAC nomenclature, carboxylic acids have an OIC acid suffix. For trivial names, the suffix is usually IC acid. Carboxyl radical. The radical COOH has only a separate fleeting existence. The acid dissociation constant of COOH has been measured using electron paramagnetic resonance spectroscopy. The carboxyl group tends to dimerize to form oxalic acid. Physical properties. Solubility: carboxylic acids are polar, because they are both hydrogen bond acceptors and hydrogen bond donors. They also participate in hydrogen bonding. Together the hydroxyl and carbonyl group forms the functional group carboxyl. Carboxylic acids usually exist as dimeric pairs in non-polar media due to the tendency to self-associate. Smaller carboxylic acids are soluble in water, whereas higher carboxylic acids are less soluble due to the increasing hydrophobic nature of the alkyl chain. These longer chain acids tend to be rather soluble in less polar solvents such as ethers and alcohols. Boiling points. Carboxylic acids tend to have higher boiling points than water, not only because of their increased surface area, but because of the tendency to form stabilized dimers. Carboxylic acids tend to evaporate or boil as these dimers. For boiling to occur, either the dimer bonds must be broken or the entire dimer arrangement must be vaporized, both of which increase the enthalpy of vaporization requirements significantly. Acidity: carboxylic acids have Bronsted-Lowry acids because they are proton donors. They are the most common type of organic acid. Carboxylic acids are typically weak acids, meaning that they only partially dissociate into H+ cations and RCOO- anions in neutral aqueous solution. For example, at room temperature in a 1 molar solution of acetic acid, only 0.4% of the acid molecules are dissociated. Electronegative substituents give stronger acids. Deprotonation of carboxylic acids gives carboxylate anions. These are resonance stabilized, because the negative charge is delocalized over the 2 oxygen atoms, increasing the stability of the anion. Each of the carbon-oxygen bonds in the carboxylate anion has a partial double bond character. Odor: carboxylic acids often have strong odors, especially the volatile derivatives. Most common are acetic acid and butyric acid. Conversely, esters of carboxylic acids tend to have pleasant odors and many are used in perfume. Characterization: carboxylic acids are readily identified as such by infrared spectroscopy. They exhibit a sharp band associated with vibration of the CO vibration bond between 1680 and 1725 cm-1. A characteristic new OH band appears as a broad peak in the 2500 to 3000 cm-1 region. By 1H NMR spectrometry, the hydroxyl hydrogen appears in the 10 to 13 ppm region, although it is often either broadened or not observed owing to exchange with traces of water. Occurrence and applications: many carboxylic acids are produced industrially on a large scale. They are also pervasive in nature. Esters of fatty acids are the main components of lipids, and polyamides of amino carboxylic acids are the main components of proteins. Carboxylic acids are used in the production of polymers, pharmaceuticals, solvents, and food additives. Industrially important carboxylic acids include acetic acid, acrylic and methacrylic acids, adipic acid, citric acid, ethylene diaminotetraacetic acid, fatty acids, maleic acid, propionic acid, terephthalic acid. Synthesis: industrial routes. In general, industrial routes to carboxylic acids differ from those used on smaller scale because they require specialized equipment. Oxidation of aldehydes with air using cobalt and manganese catalysts. The required aldehydes are readily obtained from alkenes by hydroformylation. Oxidation of hydrocarbons using air. For simple alkanes, the method is non-selective but too inexpensive to be useful. Allylic and benzylic compounds undergo more selective oxidations. Alkyl groups on a benzene ring oxidize to the carboxylic acid, regardless of its chain length. Benzoic acid from toluene, terephthalic acid from paraxylene, and phthalic acid from orthoxylene are illustrative large-scale conversions. Acrylic acid is generated from propene. Base-catalyzed dehydrogenation of alcohols. Carbonylation is a versatile method when coupled to the addition of water. This method is effective for alkenes that generate secondary and tertiary carbocations, e.g. isobutylene to pivalic acid. In the Koch reaction, the addition of water and carbon monoxide to alkenes is catalyzed by strong acids. Acetic acid and formic acid are produced by the carbonylation of methanol, conducted with iodide and alkoxide promoters, respectively, and often with high pressures of carbon monoxide, usually involving additional hydrolytic steps. Hydrocarboxylations involve the simultaneous addition of water and CO. Such reactions are sometimes called repichemistry. HCCH plus CO plus H2OCH2 equals CHCO2H. Some long-chain carboxylic acids are obtained by the hydrolysis of triglycerides obtained from plant or animal oils. These methods are related to soap making. Fermentation of ethanol is used in the production of vinegar. Laboratory methods. Preparative methods for small-scale reactions for research or for production of fine chemicals often employ expensive consumable reagents. Oxidation of primary alcohols or aldehydes with strong oxidants such as potassium dichromate, Jones reagent, potassium permanganate, or sodium chloride. The method is amenable to laboratory conditions compared to the industrial use of air, which is greener, since it yields less inorganic side products such as chromium or manganese oxides. Oxidative cleavage of olefins by ozonolysis, potassium permanganate or potassium dichromate. Carboxylic acids can also be obtained by the hydrolysis of nitriles, esters, or amides, in general with acid or base catalysis. Carbonation of Grignard and organolithium reagents. RLi plus CO2 RCO2Li, RCO2Li plus hydrogen chloride RCO2H plus lithium chloride halogenation followed by hydrolysis of methyl ketones in the haloform reaction. The Kolb-Schmidt reaction provides a route to salicylic acid, precursor to aspirin. Less common reactions. Many reactions afford carboxylic acids but are used only in specific cases or are mainly of academic interest. Disproportionation of an aldehyde in the Cannizzaro reaction. Rearrangement of diketones in the benzoic acid rearrangement involving the generation of benzoic acids of the von Richter reaction from nitrobenzenes and the Kolb-Schmidt reaction from phenols. Reactions. The most widely practiced reactions convert carboxylic acids into esters, amides, carboxylates, salts, acid chlorides, and alcohols. Carboxylic acids react with bases to form carboxylate salts, in which the hydrogen of the hydroxyl group is replaced with a metal cation. Thus, acetic acid found in vinegar reacts with sodium bicarbonate to form sodium acetate, carbon dioxide, and water. CH3COOH plus sodium hydrogen carbonate CH3COO-NA plus CO2 plus H2O. Carboxylic acids also react with alcohols to give esters. This process is heavily used in the production of polyesters. Likewise, carboxylic acids are converted into amides, but this conversion typically does not occur by direct reaction of the carboxylic acid and the amine. Instead, esters are typical precursors to amides. The conversion of amino acids into peptides is a major biochemical process that requires ATP. The hydroxyl group on carboxylic acids may be replaced with a chlorine atom using thionyl chloride to give acyl chlorides. In nature, carboxylic acids are converted to thioesters. Carboxylic acid can be reduced to the alcohol by hydrogenation or using stoichiometric hydride reducing agents such as lithium aluminium hydride. N-dimethylammonium chloride 2Cl- is a highly chemoselective agent for carboxylic acid reduction. It selectively activates the carboxylic acid and is known to tolerate active functionalities such as ketone as well as the moderate ester olefin, nitrile, and halide moieties. Specialized reactions. As with all carbonyl compounds, the protons on the alpha carbon are labile due to keto-enol tautomerization. Thus, the alpha carbon is easily halogenated in the Helmholtz-Zielinski halogenation. The Schmidt reaction converts carboxylic acids to amines. Carboxylic acids are decarboxylated in the Hunsdiecker reaction. The Dakin-West reaction converts an amino acid to the corresponding amino ketone. In the Barbier-Wheeland degradation, a carboxylic acid on an aliphatic chain having a simple dimethylene bridge at the alpha position can have the chain shortened by one carbon. The inverse procedure is the antistat synthesis, where an acid is converted into acyl halide, which is then reacted with diazomethane to give one additional methylene in the aliphatic chain. Many acids undergo oxidative decarboxylation. Enzymes that catalyze these reactions are known as carboxylases and decarboxylases. Carboxylic acids are reduced to aldehydes via the ester and DIBAL, via the acid chloride in the Rosenmund reduction and via the thioester in the Fukuyama reduction. In ketonic decarboxylation, carboxylic acids are converted to ketones. The Kolb electrolysis is an electrolytic decarboxylative dimerization reaction. In other words, it gets rid of the carboxyl groups of two acid molecules and joins the remaining fragments together.